Well, hi there. We are going to find the volumes of solids with known cross sections. Now, you're probably like, what's a cross section and why do I know it? Well, they're going to tell you what the cross section is. That's how you're going to know it. And a cross section is when you slice something and you get a specific shape. For example, if I was to slice this water bottle parallel to the base and then hold it up, well, water would go everywhere, but it would be a circle. That would be a cross section. That's the very basic definition. So let's go to this. This is what we're going to be using. And it says, find the volume of the solid bounded by the graph of f of x equals square root of x. So this little guy right here, that one's going to be f. This is the f of x function. And then g of x equals x squared. That's this function right here. That's the parabola. With cross sections perpendicular to the x-axis that are, okay, let's just stop and think about what this represents. First of all, we're going to take a knife, a ruler, and we're going to slice cross sections perpendicular to the x-axis. So here's our x-axis, and we're going to slice. And when I slice, I'm going to get, in the first instance, a square. So if you need to visualize what that looks like, let me give you just kind of a rough visualization, and then we're going to go to a different way of visualizing it. You'll see a little bit more in a three-dimensional sense what I'm talking about. This is basically a three-dimensional issue. So we're going to slice it like this, and we get squares, an infinite number of squares between 0 and 1. Of course, halfway between 0 and 2. So yeah, obviously 1 there, and we're on a scale of 1/2. And so these squares have a base that is this length. Let's use this one right here. It's this long, and that exact same length of the base is how much you would come up off of the paper. Now that may not do much for you, so let's do this a little bit differently. Here we go. These exact same functions have been graphed right here. And if it would quit spinning, move, here we go. There we go. I'm going to turn it the way your paper basically has it right there. Well, sort of. You might have to tilt your head a little bit, but that's okay. So this is what you're looking at on your paper. And we're going to click squares. And then if I turn this in a three-dimensional sense, you can see the square coming up out of it. Well, there's an infinite number of them, and you're not going to see the infinite number of them. But what we are going to do, start it back here, and we're going to, we're going to spread it out like this. Now, this is just 10 squares. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the 10th square is right here. And right here, where my mouse is right here. And the length, the distance between f and g would be 0. So technically there is no square there. But we would count that as the 10th one. But let's increase the number of squares. So we have a three-dimensional object, and this is what it looks like. So this is it, like from above, so a bird's eye view. And then from the side, different perspectives, this is it. That doesn't look exactly like a square. I think or series of squares. I think the scale might be a little bit different, but it's basically this. Notice it's square, 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 all the way across. Okay, so if I want to know the volume of this, what I'm really going to do is add together the area of an infinite number of squares. So let's just start this idea this way. I want to add together the area of an infinite number of squares, and these squares go from x values 0 to 1. Okay? Well, as we do this, we are moving along the x-axis, so we've established that, and then we're going to have some stuff in here, and we'll deal with that. So what are the shapes that we're adding together? Well, they're squares. So over here on the side, what I like to do is I like to write down the length of the side of a square, and the length of the, let me rephrase that, the formula for the area of a square. That's what I'm trying to say. Sorry, I'm getting a little confusing here. So the formula for the area of a square would be, well, length squared. You can call it s squared. You could call it base squared. I'm going to call it base squared. So now the question is, if I'm going to accumulate an infinite number of areas of squares, I need a formula for the area of a square in here. And it's not as simple as putting, well, base squared. Like, I hear you, fine, that'll work. But what is the base? What is the base of this? Let's just get one square. Let's just go down to one square and it's going to be right there. Okay, how long is this square from here to here? Now, the answer to this question, so I'm moving along this bottom little purple piece, the answer to this question from here to here is numerical, yes. But in a general sense, let's suppose that it was this square that we're dealing with, where my mouse is, or let's suppose that it was, oops, that's not working. Let's suppose it was this square. Here we go, we got it. It could be any of these squares along here. It could be this one, this one, this one, this one, this one, this one. There's an infinite number of them. So what I really need is a general formula for the length of this base. And the length of this base is, based on what you're looking at, based on colors, red function minus blue function. So red minus blue is going to give me this purple right here. So as I turn this, you see the square. The distance of the length of that base is red minus blue. Well, let's not call it red and blue, and let's turn it where we're not getting dizzy. Red and blue, it's not red and blue. It's F and G. So if I wanted, for example, this distance right there, I would evaluate the F function at 1/2 and the G function at 1/2, and then I'd subtract them. So what is the base? Base of the square? It is, let's stick with the same color, I'm switching colors so much, F minus G all squared. Now I do want to point out that it's not, let's write this down, it's not this, and it's not this. Those are different issues, okay? This is what it is. So we're going to figure out what that is using a calculator, and I believe it will work quite well. So let's just go ahead and type F is y1, and F is the square root of x, and G is y2, which would be x squared. And we're just simply going to figure this out. So math 9, from 0 to 1 of F, which is alpha trace y1 minus alpha trace y2. And then we need to square it. And oh, we've got a problem here. We need to square that entire thing, and we can't quite get where we want to go. We had some automatic parentheses that popped up here, so we're going to have to go back and put in some parentheses. And in doing so, we have to press second and insert. Second insert a parenthesis here. We'll put another parenthesis here, and we'll square that, and dx. And we're about to get the exact answer. We'll round to 3 decimal places, and it is 0.129. Okay, let's move on to the next one where we have semicircles. And we know that we are accumulating the area of a lot of semicircles. No longer are we going to have squares that come up off this paper. We're going to have semicircles. So let's switch to semicircles. Oh, you see it? You see it? There we go. An infinite number of semicircles all along here. There they are. So basically it's like you're building a building, and this is the floor plan, and the rest of the building, the three-dimensional aspect of the building, the heights, are based on semicircles. There it is right there. That's it. So now the issue is, well, and it's the same issue we had a minute ago, from where to where? Well, 0 to 1 along the x-axis. So we have dx going on here. But now I need to come over here to the side and figure out, well, what's the formula for the area of a semicircle? And the area of a semicircle would be, well, okay, the area of a circle would be pi r squared, but I don't want the whole thing, I just want half of it, okay? And that's fantastic, and you can go ahead if you want to and just put some parentheses and start filling some things in, but let's be careful. How long is the radius? In any of these given situations, how long is the radius? So let's go down back to one semicircle. And let's slide it over to here. So if I said, how long is the radius of this? You wouldn't say it is F minus G, like it was a minute ago, or red minus blue. You would say it's half of that. So in this circumstance, what I wrote right here is correct, but I just need to be careful that R is F minus G. Okay? Oops. F minus G over 2. Wow, that is very poorly written. Let's white this out and do this a little differently. F minus G over 2. Okay, so, and again, we can go back up to the first one if you want to and be like, well, B actually was F minus G. So you can do it that way. You can establish the formula and then establish what you need to plug that into the formula. So let's do that. So what I have is 1/2 pi. Oh, 1/2 pi could go here. 1/2 pi could go in the front. It's a constant, right? You can factor them out. It's one of the properties of integrals. And then r squared, so my radius squared, and my radius is F minus G over 2. This is correct. It is not wrong at all, but I'm going to take 2 steps forward and 1 step back. No, I'm going to take 2 steps forward to kind of show you how this can be simplified a little bit more, just in case this was a multiple choice item. So we have pi over 2, the integral from 0 to 1 of, let's see, F minus G, and let's do that, G squared, over, well, let's square that too when we have a 4 down there in the denominator. And then I can factor out what technically is 1/4. So this 1/4 is going to come out. And when it does, it multiplies with that 2, and I have pi over 8 from 0 to 1 of F minus G, and it is squared dx. So it's really the same answer we had here, only it's multiplied by pi over 8. So I could take this, multiply it by pi over 8, and I'd get this answer. For the sake of the concept, I'm going to move forward and not continue to solve all of them, answer all of them. I'll come back at the end and just crank out a whole bunch of answers all at once. But I'm going to move on for now. So leaving that one hanging, we're going to leave them all hanging until we come back to it. We have rectangles with a height of 2. So in this particular circumstance, this little program right here that we have, that's so wonderful, doesn't have an option for rectangles with a height of 2. So we're just going to have to come over here and figure out the formula for a rectangle with a height of 2. Well, here's the formula for a rectangle. Base times height. And the base is, we've been through this, F minus G. Okay, well, that's good to know. Base is F minus G. And the height is 2, because they said so. Move that mouse out of the way. And so we're, at this point, we're just setting them up. So we're going to have the integral from 0 to 1 of F minus G times 2. So F minus G, it is not squared. It's not squared. We're not dealing with the square, semicircle. It is base times height. There's your base. There's your height. Times 2. Okay, let's keep moving. The next one is a rectangle, base times height, with a height that is 3 times the base. Well, we know the base is F minus G, and we know the height is 3 F minus G. So if you want to get technical, and you should, this is F minus G times 3 F minus G. So it's 3 and then F minus G squared. So setting it up the way we've done the others, we'll have the integral from 0 to 1 of 3. We can put that in the front. And then F minus G squared dx. Okay. Rectangles with a height that is 1 more than the base. At this point, they're getting kind of monotonous, not monotonous. They're annoying. Make them stop. No, they're getting a little more repetitive. So hopefully you're just looking at this and saying, oh, rectangle, I know the formula for that. And then you just start thinking, what's the base? What's the height? The base is F minus G. The height is 1 more than the base. Well, it's F minus G plus 1. Okay, then do it. So what I really have is the integral from 0 to 1 of, now in your mind, you might be thinking maybe something factors out. I don't know. Let's just start writing. Maybe it does, maybe it doesn't. F minus G, and then F minus G plus 1. You might be tempted to square somebody, but these are 2 very separate things. That plus 1 throws things off. That's what we have. Nothing factors into front. Okay, let's keep moving. Rectangles with a height given by a formula. What? So base times height is a rectangle. The base is F minus G. If you don't need to write this every time, that's fine, but it just sort of helps me explain things. And the height is 4 minus x. Don't make it harder than it is. That is your height. Just go with it. So this is the integral from 0 to 1 of F minus G times 4 minus x dx. Do you want to multiply that out? Nope, me neither. Leave it. We'll crank out some answers in just a few minutes. Okay, Now things get fun. We have isosceles right triangles with a leg on the coordinate plane. All right, well, let's just start with the obvious. We know we have that much. Same thing here. We have an isosceles right triangle with a leg on the coordinate plane. So, slide up. What we have is a three-dimensional figure that is made up of isosceles right triangles, and this is one leg, and the other leg is going to come straight up out of here or out of here, it doesn't matter, and they're going to make a right triangle that is isosceles. First of all, here's what I do know. I know that I have the formula for a triangle. Okay, 1/2 base times height. I also know that the base is f minus g, right? The height of this is also f minus g, and here's why. Let me put a little paper weight down and draw a little bit. So here's what's going on. I'm trying my hardest to draw this thing. It makes sense. We have this, and this is the base. Now, what I'm going to do is pretend like this is coming up out of the paper, but I'm kind of drawing it out this way. So there's an isosceles triangle that's tilted up here, and it looks like that. Like we're just kind of looking at it sideways, sort of. This is the same as this. Well, if this is my base and this is my height, they must be the same thing. Here's my right angle. Okay, and basically what's happening is I would take some scissors and I'd cut that and I'd fold it up. It'd be all three-dimensional, right? I'm not going to do it, but there it is. So my height is the same as f minus g. So what I'm really dealing with, it's worth writing, I have 1/2 base times height, where they're the same thing, so 1/2 f minus g, and it is squared. 1/2, there's your constant, and then f minus g, and it's squared. Okay, now things get fun. Isosceles right triangles with the hypotenuse on the coordinate plane. Let me go to, equilateral triangles. They have that. They don't have isosceles. That's a shame. It's the best one. So here goes. Area equals 1/2 base times height. Now you might be tempted to be like, oh, base equals f minus g. Hold your horses now. It does, but it doesn't. But it does, but it doesn't. Okay, let's talk about it before I write some stuff. So same picture, same idea. There's f, there's g. And this time we're going to have that, no changes yet. But when I look at it from the side, so there's a guy standing right here and he's looking. And as he looks, from his perspective, this is what he sees. That is the most poorly drawn isosceles right triangle I've ever drawn in years of teaching. It's just tragic. It's awful. So this is what he sees, and this is my base, and this is my height. So yes, my base is still f minus g. That doesn't change. I was reluctant to write it, but I wanted to explain first, f minus g. But what's my height? I don't know. Let's find out. Okay, don't make it harder than it is. Let's say that this is the base, then this piece right here must be half the base. Okay, it's going to be half the base. Here we go. This little guy right here, he's half the base. Well, if this is half the base, this is the other half of the base. And based on the properties of isosceles triangles and the fact that it's a right triangle, 45 degrees, also 45 degrees. We've cut this right angle in half. So this is 45 and this is 45. So if this is 1/2 the base, then this is also 1/2 of the base. So the height is half the base. Okay? So let's come over here. The height is 1/2 of the base, which means I really have 1/2 base times 1/2 base. Whoops. Where's the wrong thing? So what I really have is 1/2 times a half, and then f minus g, he got squared. And so I have 1/4 f minus g squared. Okay, we're going to take a moment, go through these, type them all in the calculator. It's going to be a pretty quick process because I just want us to crank out answers. If you want to try these on your own on the calculator, it's really good practice, particularly since there are so many parentheses that you can mess up if you're not careful. So let's do it. I'm going to go to the second one, which is actually, notice, the first one times pi over 8. So we're just going to take that last answer, and we're going to say times. Pulls up the last answer. Once you type an operation, I clicked my fingers as if that just works for calculators. Once you type an operation, it pulls up the last answer. Just assumes you're going to do that. Multiply by that in that case. Pi over 8. And I have 0.050. Okay? Let's do the next one. Now, this is not squared, so I don't need to be pulling up previous answers. Let's just clear. Math 9 from 0 to 1 of f minus g. Calc f minus. By the way, I'm pressing alpha trace to get to those. There we go. Oops, I need to double this. I'm going to go all the way to the beginning. Good calculator process here. Let's press, this is cool. If you press second in the left arrow, it takes you all the way to the beginning. If you type the number 2 right here to get that in there, not going to work. Second, insert, doubled it. That's it. I'm going to go with 2/3 on that one. It probably just computed it as well as it could and then just stopped. But in the meantime, if you want to put like 0.667, you can. I personally think it's just 2/3, and they just only could get it so accurate. Okay, I don't know if you've noticed this. I'm sure you have. F minus g happens a lot. I'm tired of typing y1 minus y2. I really am. I'm going to create a new one. Let's go to y equals. And I'm going to create a new one that is y1 minus y2. So from now on, I'm going to let y3 be y1 minus y2. And anytime I need y1 minus y2, instead of typing y1 minus y2, I can just retrieve y3. I think it's easy. Could have done it from the beginning, but I started this process and I was like, man, I'm tired of typing that. Okay, let's do this one, which actually is this answer tripled, but we have a new shortcut, so let's use it. Math 9, whoops. 3 times math 9 from 0 to 1 of f minus g, that would be y3, and it is squared dx. There we go. Said we're going to crank them out fast, so let's start this process a little faster. 0.386. All right, the next one is the integral from 0 to 1 of f minus g. We have a variable for that. We have a function for that. Multiplied by f minus g plus 1. Let's put that in parentheses. So f minus g plus 1, and then dx. And then you wait for it. 0.462. All right, the next one, math 9 from 0 to 1. Alpha and trace, y3. And then we're going to multiply that by 4 minus x dx. There we go. Again, just cranking out some answers. Ooh, something feels wrong about that. But it is right. It is right. Negative volume? Yes, please. Believe it will. It is undoubtedly below the x-axis. All right, let's do this one. 0.5, math 9. Technically, you can't have negative volume, but you knew that. But we're still going to call it what it is. We have calculated the integral. That's what they wanted us to do. So there we go. 0.6. Whoops, 0.0. Whoa, get it right now. 0.64. And then the last one. By the way, I hope you noticed this. These two are the same. This is half of that one. I'd love to explain that, and I will in just a second. But this one is half of that, because half of a half is a fourth. So take that last answer and divide it by 2, which you could have done in your head. I could have done in my head. There we go. And just very quick explanation. if I am looking from the side at an isosceles right triangle that is sitting like this, there we go. It has one leg in the coordinate plane, and it's doing like this. This is going to be twice that one. Kind of makes sense when you look at it that way, because that was the next to last problem. That's the last problem, which is why the last problem is half the area of the next to last problem. All right. Hope you learned something. I had a good time teaching it. So that'll be it. There'll be some more problems on the back for us to work on.